In today's lesson, we're going to be looking at equations of planes. You'll see here in blue I've drawn a plane. Every vector on this plane can be written as a linear combination of our point A plus the two direction vectors. Notice here that to get to the plane, we merely had to go from the origin to the point A, and then we have our two direction vectors. These two direction vectors, by adding or subtracting any multiple of these from our point A, will derive every vector on this plane. Planes are two-dimensional, hence why we have two direction vectors that describe it. Equations of lines are one-dimensional and have only one direction vector that describes it. So let's take a look at how we can describe equations of planes. So since a plane consists of a point and two direction vectors, let's create an equation to describe it. We'll label our one direction vector D1, second direction vector D2, and we'll label our vector that goes from the origin to our point A as R0. Now, this plane consists of all vectors R0 plus linear combinations of vectors D1 and D2. Writing this algebraically, we get the vector equation of a plane is V equals vector R0 plus S D1 plus T vector D2, where S and T are any real numbers. From this, we can quickly get our parametric equation. Your parametric equation will be easy to find once we have our vector equation. To find our parametric equation, we're going to let x equal the first coordinate of our vector R0 plus s times the first coordinate of our vector D1 plus t times the first coordinate of our vector D2. Continuing in this way for y and z, we will have our parametric equation. Let's take a look at an example finding vector and parametric equations of a plane. In our first equation here, we want to find the vector and parametric equation of a plane that passes through the points A, B, and C. Drawing a quick plane here, I just plotted points A, B, and C. I'm not looking to make these oriented properly or anything like that, just a visual that we have a plane and we have 3 points on it. And you can denote a plane with the symbol pi, by the way. What we need to determine the plane, as we saw in the previous description, is a point and two direction vectors. Well, we have 3 points here, but what I can do here is I can create my own direction vectors. I can create a direction vector AB, and I can also create a direction vector AC. AB will be our direction vector 0, -2, -8. AC will be our second direction vector, 5, -2, -7. So now that we have two direction vectors, we just need a point. We can pick any one of these points here. I'll pick point A. So let's create our vector equation of our line. The vector equation of line with V equals our point. And again, in this case here, I've chosen point A, so it'll be -1, 3, and 8, plus any scalar multiple of our first direction vector, 0, -2, -8, plus any scalar multiple of our second direction vector, 5, -2, and -7. So therefore, one representation of the plane will be the vector -1, 3, 8, plus s times 0, -2, -8, plus t times 5, -2, -7. Now notice here, one thing you could do is you can scale down your direction vectors. This direction vector here is 0, -2, and -8. I could pick any direction vector that is a scalar multiple, i.e. collinear to this direction vector, and that would be fine as well. So if I divided across by -1/2, we would have 0, 1, and 4, and that just makes it easier with future problems to work with that direction vector as the numbers are smaller and non-negative. If I want to express this in parametric form will be x equals -1 plus 0s plus 5t will be -1 plus 5t. Y will equal 3 plus s minus 2t. And lastly, z will equal 8 plus 4s minus 7t. And again here, s and t are any real number. So notice here we have our vector equation of our plane and our parametric equation of our plane. Also make further notice that this equation is not unique. I could derive another equation for this plane had I chosen different direction vectors. I could have chose the direction vectors b to c and a to b, and I could have chose a different point, let's say b or c. No matter what you choose, these equations of the planes will be equivalent. All right, so in this next example here, what I want to do is I want to look at the plane that we created in the previous example. So using this plane here, we want to ask, is the point P on the plane? How about the point Q? So what does it mean for a point to be on a plane? Well, for a point to be on a plane, it must mean the following. For instance, if point P is on the plane, therefore 14, 1, and 3 must equal our point, plus there must be some s value such that when multiplied by our first direction vector plus some t value, which then when multiplied by our second direction vector and summing all of this up must equal 14, 1, and 3. So this will generate some equations for us. Notice, first equation says 14 must equal -1 plus 0s plus 5t. Our second equation says that 1 has to equal 3 plus s minus 2t. And our third equation says that 3 must equal 8 plus 4s minus 7t. For equation 1, we get 14 equals -1 plus 5t. Solving for t here, we get t equals 3. Substituting that into equation 2 and solving for s, we get s is 4. So therefore, the parameters of s being 4 and t being 3 are the parameters we need so that 14, 1, and 3 is on the plane. However, we must check to see whether these two parameters satisfy our third equation. Checking this in our third equation, we see that the left-hand side will equal the right-hand side, and therefore 3 equals 3, and therefore this point is on the plane. Let's take a look at point Q. So checking point Q on this plane here, generating the exact same equation, notice the first two coordinates of P and Q are the same, so therefore it's going to yield the exact same equation, and therefore the exact same S and T parameters that are required. Subbing this into my third equation, we get that 5 is not equal to -9, and therefore point Q is not on the plane. That concludes today's lesson on vector and parametric equations of planes. Thank you.